So let's continue with sinusoids. I think it's going to be a quick lecture today, just to move on with to finish this topic, and then we will go into more details about doing calculations for complex numbers and complex exponentials. Do you recall why we're doing this? Why we're going back to sinusoidals? We need to make sure that we can represent any signal by its components. And if you remember from the lab yesterday, we were able to get from a composed signal the frequencies in it. And each frequency is a sinusoid. And that's what we would like to look at. We talked about this, the unit circle and the radians, and what are the signs of each value in each of the quadrants of the unit circle. But the important part is this: phase and time shift. Remember, we have two types of shifts, time and phase. And time, it is represented by xt minus t1. And the phase shift, if you have in the angle of a sinusoidal signal, you have a phi. To recall, this is the angle, this is the radian frequency, and that is the phase shift. And if you break it down, you can say, well, are they the same? If you have a time shift and a phase shift, they actually, each one of them will be resulting in the same thing, but we'd like to see the relationship between time and phase. That's the key. So we can write the a cosine w0 and replace every t with t minus 1, and you introduce a phi on the other side. So originally you will be having cosine w0t, right? That's our original signal. Now, replace every t with t minus t1, and also add to it a phi on the other side. And let's see the relationship between the time shift and the phase shift to represent those. So you can represent it this way: replace every t with t minus 1, and then you can get the w0 inside the parentheses because it's distributive. And then you have the phi, and when you what you end up with is the angles. So this angle here equals to this angle on the other side. From these angles, you can see that minus w t1. So you can replace this and replace that. See this from this equation here. This is w0t, right? Move it to the other side and change its sign. You'll end up with w0t minus w0t minus w0t1 equals phi. This will go with that. You end up with minus 0 wt wt0 equals 5 phi. That's 1, right? That's 1. And that's the relationship between t1 and phi. So the phase shift and the time shift, this is the relationship between them. So if you want to break it down, you can say my t1 is equal to this here, right? By dividing phi by minus every side by w minus w0, and you end up with this. Or you can replace w0 with 2 pi f. This is the radian frequency. This is, do you remember what that thing is? This is the cyclic frequency that we call it, f. And that's the relationship between all of them together. And you will end up with what is phi with respect to the time shift and what's the time shift with respect to phi. So that's how you put the two together. A positive value of t1 is a negative value of phi, right? And a negative value of t1 is a positive value of phi. So they are the inverse of each other. And then you can look at the signal if it has, remember, a delay or an advancement into that thing. So that's the relationship between phase shift and time shift. Note that positive value of t1 equals a delay. Remember when we have cosine, w t minus 5. This means that it is actually shifted, delayed from the 0. So this is when it's only w0 t, and if you make t minus 5, you're moving it this way. So the peak is delayed. So it's going to be here, let's say, right? This peak will be moving there, and that's a delay for the time. So that's a positive value. A negative value is going to be an advance. So if you have minus minus 5, which means positive 5, then it's going to be in advance, which is plus 5. And I'm going to show you a couple of examples here to do that. A positive value of phi equals an advance, and the negative value is a delay. Right? They're the opposite of each other. Here, this is an example, and let's see if we can follow the example. This is 5 cosine 2 pi 50t plus phi, right? If phi is pi over 2, that means that it's a positive phi, means that it's going to be advancing, right? Phi 0, that's here, the original, and phi equals minus pi over 2, that's negative, which means it's going to be a delay. Now, advance going forward, delay going backward, the top, the peak of the sinusoidal. Pi over 2 is positive, advance, so it's going forward, right? If it's negative, minus pi over 2, that means that it is delayed. So it's going for at the peak. It's not here, it's now delayed. It's happening later in time. So that's the relationship between the two. Let me show you an example, and let's do it together on MATLAB. So go to computers, and let's type this code in the MATLAB, and let's look at the signals. And I want to show, we are practicing MATLAB as much as possible just to get familiar with it. And I would like from all of us to go and to write this code, and then we'll come back to discuss the output together. Okay. Let me give you some time to write it as it shows here in an M file. To make sure that we are on the same page for the code, I changed the create vector is a comment, so I added the percentage sign as well as the create sinusoid. Now, all of the functions here, f is small letter. This should be small letter if it's consistent, or if you kept it capital letter, you need to make sure that all the frequencies are capital letters for those. So let's go into what are we looking at. So you did a time, right? And the time vector is your x-axis. So here you start from 0, right? You start from 0 and you end at 0.005, but each time you do this increment, which is 0.0001. Very small increments, right? Which means that we have a lot of samples between the two. And that's how actually you define time. Starting, colons, and then step, and then the when you end with the time. Now, your frequency is 400, which means what is your t? Is 1 over 400, right? That's how much, you know, the period in which the sinusoid will repeat itself. So we're good with that. Now we would like to look at three things. A signal without shift, signal with a negative shift, phase shift, and one with positive phase shift. So what you did here is that you said cosine 2 pi f time, right? There are no phi's here. So that's your original signal, and when you plot it, it's going to be this one here, the blue, because it starts at 0, at 1 when it's 0. Cosine 0 is 1, and it goes all the way as sinusoidal. Now, if you have plus phi, so we say cosine 2 pi f time plus pi over 2. So I'm adding pi over 2 shift, and you do hold on the first image, and you try to plot it, and then you do the minus phi, which is pi over 2, and then you plot both of them. This one is going to be red. Now the plus pi is going to be this one here. Notice it's advanced. It's going to happen earlier. The peak is happening earlier here, right? So that's advanced. So if it's positive, it's advanced. If it's negative, the minus, which is the green here, it means it's going to be delayed. So the peak is happening after time equals 0, right? And this is the opposite of what happens with the time shift. But this is how we are looking into the phase. If it's minus pi over 2, that means that we are having the delay. If it's positive, it's happening advanced, earlier, right? And that's actually similar to what's happened with the time, plus t or minus t. Minus t is a delay, and plus t is in advance. I just want to make sure that we see the phase shift effect on a sinusoidal signal, and that's how it looks like. Now the time shift, note the positive value of t equals to a delay. Remember, we are talking about this here. So that's shift, and if you do shift by 0.25, the first one, this is 0.5 second, you're also delaying the signal, right, in time. So positive value of t equals a delay. We're good? Now, the positive value on phi was an advance. When we did pi over 2, it was happening earlier than time equals 0, t equals 0. And that's 0.75, and that's 1 second. That's how it's happening. When you have 2 pi, then the sinusoidal waveform does not change because the period is 2 pi. So the phase shift, if you are adding, instead of our example, we added pi over 2, correct? In the one that you did in MATLAB. If you add 2 pi, it's going to be the same signal. Nothing will change. So no delay, no advancement. This 2 pi, which is 360. Remember I told you that we have the, this is 0 to pi, and this is 2 pi. So that's 360 degrees. You're going back to the same signal. So if the phi, the phase shift, not the time, the phase shift is 2 pi, the signal is the same. It's not changing because we have two periods of 2 pi. Adding or subtracting multiple of 2 pi does not change the waveform, so we don't see any delay or advancement in the signal. And now this is 2 pi is called the modulo, or this is called the modulo of 2 pi, at which the signal repeats itself, and we don't have any delay or we don't have any advancement. Over the sampling problem that we did before, let's go and write this code in MATLAB, and you don't have to put the greater signs in your file. Just create a new file and you just put all of these. So if you recall, what is the Nyquist threshold? It has to be twice the largest frequency in order to be able to have a signal that you can reconstruct without losing information. Yeah, let me give you some time to write the code. Do this, and yeah, the frequency will keep it 400. This is not, you don't need that, and you don't need any of the greater signs, you know, and then you can get this image. And we're starting from 0 to 0.005, and every time we do increment 0.001. How many points do you think we have? Yeah, look at the right side of your MATLAB and look at the time. How many points in time as a vector? You can do this by looking at the MATLAB, or you can divide 0.005 divided by 0.001, which is actually 5. Hold on, it's 6. Because it starts 0, yeah. 0.001, 0.002, 3, 4, and 5. So 6 points, which means that it's a very, very small number of points to get the data. So it's not even a sinusoidal. You can tell. And then you did the figure and you plot the figure. And that's the importance of sampling. If you are not getting enough points, you're losing the signal, and we can't reconstruct it and make sure that it's what we would like to be able to. So moving on to the plotting the sinusoidal signal. So we have cases. Here you have cosine 20. So this is your signal, right? Here. And I want to show you a couple of cases of what we are looking at here and what kind of information we can extract from this signal. So your amplitude is 20. We good with amplitude? And your frequency is 40, right? Because 2 pi f, that's f. And your phase shift is minus 0.04 pi, right? So the basic calculation, 20 frequency, the period 1 over f, right? So how many seconds we have a complete cycle? That's 25 milliseconds. The phase angle shift, that's your minus 0.4 pi. That's your angle or phase shift, but you can write it in radians by multiplying 0.4 multiplied by 3.14, the pi, right? Now, the calculation of the time shift, you always do this. You take the, as I told you in the previously, you take your phase shift and you divide it by the radian frequency, right? So this is minus 0.4, you just take 0.4 pi and you divide by 2 pi 40, and that's going to give you the time delay. So every 5 milliseconds we have this time delay. That signal is, so it's 5 millisecond delayed, so the peak is 5 milliseconds delay, which is, going to the right here, this way. So this should be the original one, right? But because it's delayed, you're going to be, the peak will be here, well, that distance between the two is 5 milliseconds, right, delay. Now TS over the T period here, it should be 0.2. We care about this, and that. So let's say studying the frequency, let's say the frequencies of EMG, right, of a healthy subject, and you would like if there is a phase shift for a disease subject. Inside this instrument, there should be a MATLAB code or a code running that calculates these things for you, for each of the signals in your spectrum, the frequency spectrum. This is an example, a numerical example by how to plot a sinusoidal signal. By having all the values, you can have time, you can have the angle, and you can have the entire value of your signal. So you can do one by one, each one of them, and get the values of it, where it should be. But also you can find the delays. For example, here, if we are dealing with the previous one, you can find the period, one cycle, how much time that cycle is, and then you can find the time shift, which is it's a cosine, correct? So it should start here, right? The peak, but you can find the distances and you can measure how much you have phase shift and what is your cycle, and then you can get the period and all the information that you want from it into plotting it. So this is what we're learning is ways of how can we plot the sinusoid by learning about the period, when it repeats itself, and learning about the phase shift to know where all the time shift and where that thing is. This is another example, and again, so we don't have any phase shift because the whole thing is without phi, so the angle is without a phase shift. You can calculate the amplitude, the frequency, the period. The phase shift is 0, right? We don't have any phase shift. And then you can calculate the time shift. You put 0 on the top, as I mentioned to you, the phi, and then you divide it by the radian frequency, and it's 0 points. So when you plot it, it starts here, the top. But you need to know the period and all the other information so you can plot your signal. Now this is another example where you have a plus instead of minus phase shift. So that should be an advance, correct? Remember we said it should happen earlier. A negative phase shift is going to be delayed, and a positive phase shift is going to be an advance. You do the calculations, amplitude, frequency, period, phase shift, time shift, we're good to go, right? With that, and because it's advancement, it's happening earlier, right? So that's where it should be on the 0, but it's because we have a positive phase shift, should happen earlier into that. And then you can do the calculations, the one that you want to. Do MATLAB one more time. So let's create a function now. Remember we did this last time? Open a new M file, and you start with function, and the function is going to be cosine plot phase. So it's going to plot you the cosine signal. And yeah, let's give you some time to write this thing down, and then we'll talk about the output, how that will look like. Always remember the name of what is the name of your file should be. It should be this .m. If you're doing a function, the name of the M file should be the same as the function name. Otherwise, it's not going to work in MATLAB. Now remember, MATLAB is case sensitive. So if you have frequencies like this with F capital letter, make sure that the first one is capital letter. Alrighty, so just to make sure that we know what we are talking about here, you need to comment this. You don't need that, and it should be green, right? So that it's all green. Just to make sure that I remember this. That does not need to be there. So you created the function that plots the cosine phase and with phase for you. So you write all of this into a MATLAB function, MATLAB file, an M file. That's what we call it. And you name the file with the name of the function .m. And when you write this thing, you save it. After you save it, you go to the command line, and when you call it, you can call it like this: cosine INE plot phase, right? And then you add, this is in your on your command line, and then you can add the values. Let's say 40 hertz. You can have amplitude of 5. You can have the phase of pi. That's the phase shift. You have, let's say, 100 points, and then you start time from 0 and you end, let's say, at 2. And you call this, and you will end up with a figure showing you the sign. Now here it just, applications of how we are plotting, and similar to what we did before with the cosines and the sines. So what is so important about sinusoids and periodic signals? Why it's important for biomedical engineering? Remember, any periodic signal that's important, like an ECG, can be broken down into a summation of sinusoids, a lot of sinusoids. And these sinusoids, you can look at the frequencies by having the Fourier transform. Instead of looking at the time domain, I can look at the frequency domain, and I can tell, which frequencies are there. Now, if you want to do filtration for signals, and there is a noise with a specific frequency, you can design a filter to remove that frequency. So that's why we like to use the frequency domain and break down to the sinusoids in order to be able to do filtering and remove noise, and also simplify our analysis. And you're going to learn how to use it also in imaging. So what is important about sinusoids for us? Here's the thing. Our signals in nature periodic. They're usually not, right? But the ones that we try to deal with, especially in healthcare, sometimes they are periodic, like an ECG signal. Name some, so what kind of signal do you think can you come up with when it comes to vibrations? Speaking is vibration, right? Because we are vibrating the sound, the air around us, and that's how it vibrates. Another example is ultrasound imaging. It's vibrations, right? Anything that vibrates, that's for us. Voice is also, when I speak, I have frequencies. We call the pitches. So I have high pitch or a low pitch. If you are a singer or performer, each one of them, they have their bandwidth of frequencies. So some people are to the low pitch and some people are closer to the high pitch. So you can analyze that frequency. Now, there are a couple of studies that are saying that I can detect disease by your frequencies, the voice frequencies. Yeah, so you can make some. Remember when you have a cold, see how your voice change immediately? We have algorithms that can actually tell you what is happening. You need to have a big data set of healthy people and then people at different diseases, and you can tell the algorithm that if that frequency is there, that frequency bandwidth, those number of frequencies are there, this is the disease, and then it can do that for you. And remember voice recognition? That's another application for this, for the frequencies. So if I'm speaking, you can have my voice as a password for something. It detects the frequencies. So what's doing? It's breaking down the voice into sinusoids, and each sinusoid is a specific frequency and detects which one is which. And then from the phase shift, that could be your disease state or how people can be, how the voice can be categorized or segmented. Now, electromagnetic, the electromagnetic, we have something called infrared radiation from our skin, from heat. We have infrared, wavelengths in the electromagnetic spectrum. We did this a lot when we had the COVID. So we designed a lot of infrared scanners to detect when people have fever. It's all frequencies. I'm looking at the frequency and break the signal into sinusoids, and I'm seeing which frequencies do we have. And then how much phase shift or time shift it can be detected there. And biomedical, now this biomedical is a lot of application, ECG, right? It's a periodic signal, quasi-periodic, but we can find the frequencies and then detect if something happened. Now, EEG, something called sleep apnea? That's a problem. People could die and be suffocated because of sleep apnea, which means that their tongue is blocking the airflow, and that affects the brain. So we can look at the EEG signals, and we can do frequency analysis and break it to sinusoids, and we can see when someone is having high risk of sleep apnea or seizures. So sinusoids are very important for us to look at these things. But all that analysis should be your code, MATLAB. So you see your MATLAB code that you wrote, the functions, you can export them as a .exe file. Do you know what's an exe file? When you click on the Word document logo, it opens the Word, right? The Word editor. You can create your code as a icon. When you click on the icon, it runs. And that's what they have on the software. When you go to any hospital and you look at a screen, they have these icons, but each icon is actually an executable file of an M file or a MATLAB file. And we want to learn how to do that together to create your own. So all your function can be actually exported as an icon, and then you can have the execution file. So that's in your design for the device. So are signals in nature periodic? Not always, but we may be able to model them with periodic signals. If it's periodic, immediately you can break it down into the sinusoids that makes that signal. Example, we have measured blood viscosity. That's something that we use a lot of frequency responses and sinusoidal simulations for it, and also the measure of cell mass. So not just only the system, like the respiratory system. No, we can look at cells and we can study those things. I think we should stop here, and we'll come back and continue later on. Now, I know we didn't finish the multiple choices, but I will, at the beginning of next lecture, we'll go through them together, and we'll make sure that we're all on the same page. Sounds good? Thank you so much.